So thank you, firstly, for inviting me to give this set of talks. I think it's be a great opportunity to get feedback from all of you about some of the things we have been doing. This is work with Lawrence Eberhardt and Matthias Geberdiel, most of which has appeared. So maybe at the end of it, if I get time, I'll say something about things we are thinking about right now. But the plan of the talk is firstly to give a little bit of a bird's eye view of the lectures. Well, at least more some motivations and then some sort of general picture of where we are getting to. Today I hope to cover the context in which this will be done, which is the AdS3 CFT2 in a particular tensionless limit. And by the way, is this for people who are at remote parts? Is this visible? Should I write a little bigger? The message takes a few hours to get.
Navamita, can you hear and see? Yes. Okay. Good.
So yeah. So roughly the plan is today I hope I'll be able to come up till here, and tomorrow I will tell you more about trying to derive this correspondence. And finally, if there is time, I will indulge in shameless speculations, and we'll see and various other half-formed thoughts and so on. So firstly, let me start by saying what I mean by does it mean to derive the AdS CFT correspondence in general. AdS3 CFT2 will be some specific example. But so I think in the 20-odd years that we have all studied this correspondence, it has still been a very mysterious or magical or whatever, a very miraculous even sort of relation between two hitherto unsuspected theoretical frameworks, namely that of gravity, quantum gravity or string theory, in most of the cases string theory, and on the other hand, conformal field theories or quantum field theories. These are structures which, in a sense, are well-defined, mathematically well-defined. I will restrict to the cases of the AdS CFT correspondence where there's a perturbative string description. So there are others. Of course, there's the AdS7 n times S4 example and so on, where perhaps there isn't one. But in any case, perturbative string theory is well defined, at least in principle, in terms of the rules for a two-dimensional nonlinear sigma model. So it's there's a more or less defined prescription to study these backgrounds in AdS spacetimes. Of course, this is technically difficult in the case of Ramond-Ramond fields, and perhaps, I think more needs to be done there, but in principle, there exists a well-defined mathematical description for perturbative string backgrounds. So that's one side, that's one part of the correspondence. And the other side is quantum field theories of the kind that you study. mainly CFTs, of course, starting from CFTs, which you can define in some Wilsonian sense by autonomously. So these are two autonomously defined entities, and there's a relation between them, and this relation between them. And since we are looking at perturbative string theory, we have in mind CFTs which have a large n expansion, and there is a dictionary between these two sides, and it's a growing dictionary. It started with Euclidean correlators, but went on to other kinds of correlators, then non-local objects, Wilson loops, defects, various sorts of entities like that, and even things broader than that nowadays, like the entanglement entropy and so on, which are not even observables in some canonical sense. But there's a growing dictionary exhibiting the equality of these two sides. So deriving this correspondence, at least for me, means to exhibit this mathematical structure, that the fact that these two mathematically well-defined entities are secretly the same, to make that manifest, to make it just be there in your face. So that, in a way, is for me sort of an operational definition of deriving the correspondence. I want to also stress in this context that deriving is not for convincing oneself of its correctness. Maybe that, I think, I think most of us don't doubt its correctness. It is more, it's more an attempt to understand the inner mechanism of how this works, rather than that whether it is correct. And I think this is important, and not just understanding that mechanism, how the mechanism works is important, because I think by looking into the sort of moving parts, if you wish, of this correspondence, you can try to study how general this correspondence is. Is it true for cases only with supersymmetry, but there are other cases too? So what is the boundary of the domain of AdS-CFT correspondence? Is it true for large NQCD? It is, and so on. So it'll hopefully enable you to construct new examples and go beyond existing ones. And eventually, by understanding this, I think one might hope to get a deeper insight into quantum gravity itself, and which people are trying to make sense right now in terms of how the bulk encodes the bulk. The information in the bulk is encoded in the boundary. I think having a sort of nuts and bolts picture of this correspondence will enable you in the ideal case to figure out what is going, why quantum gravity, at least in anti de Sitter spaces, is described holographically, and perhaps then allow you to describe in more general spacetimes as well. So this is sort of the broad philosophy of why deriving the correspondence is an important thing. It's not some kind of exercise in mathematical physics or something like that to do this. So, yeah. We know examples. All our understanding of AdS-CFT is through examples, most of which are constructed through D-brain constructions in string theory. So we don't know, I mean, if you say let go of that original D-brain construction method, it seems to suggest a more general set of dualities. So is it true for large NQCD, for instance? I mean, is there a well-defined string background? What is the largest set of such, at least let's say in perturbative string theory? Maybe then there'll be M theory type of things, but.
If you take this point of view that it defines the CFT to define quantum gravity, then from that point of view, what does it mean?
Of course, then I mean, the whole idea is there are two independently defined quantities, and then you get something non-trivial out of it, because there will be regimes where one is more easy to understand, and with respect to the other, you'll get insight about one side from the other.
Turn it around. Like, I mean, you can look at weakly coupled string descriptions, like 2B theory in flat space.
Yeah.
Does that have a good quantum description, boundary quantum description? What is it?
Yeah.
Yeah. A huge moduli space of string compactification.
Yeah.
All of them.
Is it true that all string theories are described in some?
Define this other. I'm to define the other thing by that.
The other thing, but
No, but what? So in flat space, exactly what is the proposal? There's no real proposal. But even within, yeah.
Not in flat space, I mean, just sticking to this radius.
Huh. But even there, we don't often know, right? I mean, let's say many of the constructions that Sandeep, we don't know what is the dual CFT. We don't have any clue of how to define that. So, and so would like to, I mean, so of course, then that's sort of defining away the thing. I mean, it's not, you don't learn about this thing.
But
So, so a concrete goal, I mean, so this was very broad philosophy, and obviously I will not get anywhere near it, but the concrete goal, to narrow one's goals and one's this thing to make some progress, would be to tackle, firstly, so various levels of narrowing that I'll now do. So the first narrowing is to look at, firstly, a class of observables. And I think Euclidean correlators is a large class, and I think understanding that and hopefully will lead to understanding other things. So there you can make a more or less, this is still somewhat schematic, but a kind of a more mathematical equality that you would like to demonstrate. So what is this equality? On the left-hand side is what you conventionally call a string scattering amplitude. An endpoint amplitude, which involves vertex operators on a world sheet, which are labeled by positions. So Zi for me will always denote world sheet coordinates. So Zi's are positions on the world sheet. These vertex operators are labeled by a space-time label, which is in the case of asymptotically AdS, spacetimes is a label on the boundary of that AdS. So these xi's will label for me the boundary of AdS. And there are other labels on this. So hi, so h1 to hn. So hi's are the conformal dimensions of the dual operators. In the language of AdS, these are just some energies or masses. They label some masses or energies. And then the W's form at the moment are some additional quantum numbers. They'll have a specific meaning in the case I will study, but at the moment just think of them as some additional quantum numbers. But so a vertex operator, as you all know, in string theory corresponds to the object that creates a physical excitation. This correlator is an endpoint function on the 2D world sheet theory. I mentioned the nonlinear sigma model. So it's a correlator in that nonlinear sigma model, defined in general on a genus G surface with n of these marked points or punctures. And the string prescription is that, you sum over all the possible world sheets, which is essentially an integral over the so-called moduli space of the genus G Riemann surfaces with n boundaries. So this is defined on a genus G Riemann surface with these punctures. So these Z1 to Zn are among the moduli, but then if you're on a higher genus surface, there'll be additional moduli. You integrate over all of them with some well-defined measure and all that. I'm not talking about that, but so that is the definition of the string scattering amplitude in AdS or in flat space. I mean, I'm sort of putting in AdS here by putting in some labels, which are labels on the boundary of the AdS.
Giving both the x's and the h's is confusing me a little bit. For example, in flat space, in instead of the x1, xn, etc., I could have worked with k1,
Yeah.
kn, etc.
Yeah.
And then the corresponding age would be just k square by 2.
Yeah, so here it's one less. So that's why you're this thing. So there is the energy and there is the, so this is one less than the number of dimensions. So in a sense, if you Fourier transform it or something, it's the right. Yeah, I'm coming to the right side in a moment. So this is the left side, which is the string scattering amplitude. It's a mathematically more or less well-defined quantity, right?
When you write it in this way, you assume that the on-shell condition has been imposed.
Yeah, yeah. These are all physical states, so these are the things where the on-shell condition has been imposed.
So just to clarify, so xi's are the points on the boundary,
Yeah.
and zi's are the conformal coordinates on your Riemann surface. That's
Yes. So there's an embedding of the Riemann surface into your target space, which is the whole AdS, and there might be actually additional pieces also beyond the AdS, but and these yeah. So there's an embedding of this Riemann surface into that whole AdS space.
x's, these are points from which your
Yeah.
where you position your operators.
Yeah, exactly. So, so it's a scattering amplitude. So you're thinking of this in AdS as coming from the boundary of AdS, and then it's coming inside doing various things.
Is it okay to think of hyperbolic space instead of AdS?
Yeah, so I'm actually looking at Euclidean correlators. So that means that basically I'm looking at AdS as Euclidean hyperbolic spacetime. So space. So. So the right-hand side is what you would call the field theory or the CFT correlator. And I will mostly now also talk about CFTs. But so here they are labeled by operators in the CFT, which are in the physical spectrum of the CFT. So the H's are labels of that spectrum. So there's a dilatation operator or whatever Hamiltonian. And these H's, which correspond to those H's, are in the are the spectrum of the operators. There are additional quantum numbers. Operators are labeled inserted at positions x1 to xn on the boundary of that AdS spacetime. And you're computing a field theory correlator, a CFT correlator. Of course, when I write, so this is the left-hand side, this is the right-hand side. Now, to make a statement of equality, I'm assuming that there's a 1:1 correspondence between these vertex operators and these physical operators in the CFT, which is the statement that firstly you have to have the spectrum or the two-point function should agree, and then you can talk about the endpoint function. So you assume that firstly, a precondition for even proposing such a equality is that there should be a map or a correspondence between the physical states in your string theory and the operators in your CFT. And now this side, the question Mahan asked, so here this was in a genus G Riemann surface with n punctures. Here you have an endpoint function in your CFT. Typically, we are considering, as I said, this is a perturbative expansion. So this is the perturbative genus G contribution corresponds to a genus G contribution in so-called large N expansion. There will be some appropriate expansion in a parameter in the CFT, which it's typically 1/n, and that has a similar genus expansion. You pick up the so if you wish, there's a family of CFTs labeled by n, and then you can, all these correlators appropriately normalized, have a expansion in powers of 1/n, and there is a genus expansion of those correlators. So you can pick out the genus G part, and it is that part that you are claiming should be equal to this. Yeah.
Mostly I'm familiar with just say flat space or some flat space and some Calabi-Yau kind of situation, and there the vertex operators say are labeled by the momentum in the non-compact directions, etc. When you label them by the positions, what precisely do you mean? So there is of course a CFT in the boundary in the bulk. I
which can be labeled by many labels. For instance, in AdS, I could have the analog of momentum space would have been to expand in some spherical harmonics or something. So supposing even in the more familiar case, supposing you had an S3 or S2 or something in your compactification, then you would expand in spherical harmonic modes rather than momentum modes, and it would be in terms of there would be an expansion in some YLM theta phi, but YLM theta phi you can sort of just a different basis to rewrite it as some linear combination in terms of just the coordinates on the sphere. So I can take.
So your worldsheet fields, which you label by the x's.
Yeah, exactly. So the x's are playing the role as momentum in flat space. That's all. And as Gautam pointed out, because they are on shell, they are really one lower. There's one less of them than you have. Yeah.
My earlier question was roughly like, this question mark can be interpreted in two ways. One is that whether that string scattering amplitude is equal to a correlation function in a CFT that you know, it has an alternate definition, or is a correlation function in some CFT.
In some CFT, yes.
So the second question's answer, is it trivial that it has to be?
I think it has all the properties. It's not completely trivial. I think it has definitely some of the properties that you would require of a CFT. Whether it satisfies all the properties, okay, but if it's a consistent string theory, perhaps it is there. There's the whole thing about if you have an effective field theory, then there are perhaps things which are in a swampland which don't satisfy this thing. But perhaps a perturbative string theory, there might be something non-perturbatively not complete or something, but yeah, but I would expect that it should, but I don't think it's trivial to show it even.
For instance, n has to turn out to be an integer, which perturbative string theory might turn out to be.
Yeah. So so I will this thing, yeah. So go on.
So this correspondence between PHI and OHI.
Yeah.
Just can you give one example?
I will devote myself to one example only in the rest of this talk. So essentially it will be, so the string theory, as I said, there's a mathematically really well-defined worldsheet. When there's a well-defined worldsheet theory, there are conditions on what the spectrum of the physical spectrum is. It is given in more pedestrian ways in some Virasoro conditions or something, but more abstractly in terms of some cohomology. So there's some physical spectrum that you can define for that worldsheet theory. And that's, if you wish, in the non-interacting theory, the free spectrum. And that spectrum, you need to show that there's a 1:1 correspondence between the set of
Supposedly some operator
of the Hamiltonian, let's say. The space-time, there is in AdS, there is a time translational isometry, and there will be states which will be eigenstates of this thing, and there should be a 1:1 correspondence between the spectrum of that operator and the spectrum of the corresponding operator here. So the simplest, this thing of AdS CFT is equality of the spectrum of two Hamiltonians. But it is more than that. It is actually a statement about correlators also. So you have an equality of the spectrum is your starting point for then trying to this thing. So what I will in a way do today is look at a particular example and try to tell you why the spectrum in that example matches with this thing. And then tomorrow I will talk about the matching of the correlators.
For example, is there something between the Laplacian and the green function would that be something to start off with? Laplacian in the bulk
Mm-hmm.
on functions, for instance, and you look at green functions between
Yeah, so in some ways, yes, when people consider the simplest example, when the bulk theory is actually not a full-fledged string theory, but a supergravity theory or a gravity theory, and then essentially it's the spectrum of some Laplacian on the bulk, which you're equating to a set of operators in the boundary theory.
Very nice. So the left-hand side, that's a voluntary description. So I mean, does it refer to any particular background?
Yeah.
So
It is
some
an
semi-classical-
absolutely. So there's a string background which is specified by some critical CFT. Yes, I should have
Nice.
said that. It's there's some usual C equal to 0 string theory background which has a AdS d+1 component in it. Yeah.
I see. That's what I.
Yeah. So I'm narrowing it to those set of cases where there's a AdS d+1. So the background is some AdS d+1 times something such that the whole thing is a critical string background.
So you, so this is just trying to understand again. You only need asymptotically AdS, or you need genuine AdS as well?
Yeah, you basically for there would be a generalization of this for asymptotically AdS cases as well. You can think of them as some excitations of the original AdS. This thing. So, yeah. So, but I will stick to actually AdS. Okay. So, as I said, so what I will do is focus on a very specific case of a theory in AdS3. As I said, the idea will be if we can even uncover this to some extent in one example, hopefully that will have lessons for us for the general case. So what I will talk about is an example, firstly in 3-dimensional AdS and 2-dimensional CFT, but also there in a very specific limit, which I'll explain as I go along, tensionless limit. And there I will try to convince you today and tomorrow that we can carry through this program by what we will essentially do is just programmatically what we are doing is we'll start from the left-hand side and try to rewrite it in a way that it will become the right-hand side. So we'll start with the left-hand side, go to the right-hand side. If I have time at the end, I will try to explain why this is actually in sync with picture I had developed some many years ago in trying to start with the right-hand side and going to the left-hand side. But yeah, anyway, we'll see as we go along. So, all right. So tensionless limit. So let me draw a diagram. I think I've drawn here many times before. But it's just a useful way to capture things. So I'm drawing on this axis sort of space of theories, let's say simple theories, which are labeled by some one marginal parameter and this parameter n that I said, so I'll plot it against 1 over n. So this is n goes to infinity limit. So this regime is what you would call classical string theory. So because 1 over n is will be like GS. 1 over n will be like the string coupling. So 1 over n near 0 is perturbed. This is the sort of perturbative of classical string theory in this regime. This regime is what you would call free, in some sense, Yang-Mills, but free field theory, this free CFT, because this coupling lambda I will take as the parameter for the, let's say, G Yang-Mills square in simple examples. And lambda equal to 0 is the free theory. So this is the perturbative regime. So no, lambda is the 't Hooft coupling, G Yang-Mills square n.
Lambda is not G square, right?
lambda is G Yang-Mills square times n, the 't Hooft coupling. So it has, it's the thing that doesn't have n dependence, but I mean, yeah, you know. So you have this, but this is the usual regime, of course, where people focus on the strong coupling regime, the supergravity regime, and of course n large. This is where the string theory simplifies into having just some simple set of states, which is given by Einstein gravity and plus its counterparts, supersymmetric partners. So this lambda can be viewed as something which is proportional to alpha prime inverse or string length inverse to some power. So this essentially is the limit where the string length is going to 0 if the string tension is going to infinity, and so therefore the stringy excitations are not there, and that's why this regime is simple, and of course a lot of work has been done. So often I draw this diagram advocating that, well, there's one lamppost there, but there's another lamppost. And while, of course, people are often in this lamppost and looking at the shadow there, there's another lamppost here, which you can also explore its shadow regime a bit. And that's indeed where I will start from here. We'll be sort of in this, working in this regime.
So that's supposed to be a coupling constant?
1 over n, or this G? Yeah, it is the string coupling constant. It is the parameter which labels the higher genus. It's the formal parameter for expansion of the genus. So I will be, as I said, free Yang-Mills on this free CFT. This, by the way, is what you would call a tensionless limit because it's the opposite end where the string tension is going to 0, if you wish, in units of the radius of the AdS, the radius of curvature of the AdS by string units. This is going to 0. So that's why because lambda is essentially like this. This is lambda is proportional to some power of this. So this is going to 0 is the tensionless limit. So or sometimes it's called the small radius limit of the AdS, etc. So essentially the AdS is very stringy there. This is the regime where the AdS radius is very large compared to the Planck scale and so on, and the string scale. But you can apply classical gravity. But this is in the opposite regime. It's a highly stringy regime. So Einstein gravity and so on are no guides to the behavior. So this is sometimes. So one of the reasons I think this is particularly nice to study, apart from being a nice lamppost, is that this regime is perhaps one that can be, I think there are many indications, growing indications, that this is described by a topological string theory. So it's a kind of an unbroken symmetry phase. So there have been ideas from 30 years ago, people speculating that there's a phase of string theory with unbroken symmetry, or very large unbroken symmetry, which is sort of topological phase. And I think there's growing realizations of that idea, and we'll see a lot of it here. And that makes it, I think, a good starting point, at least probably a tractable starting point, also from the string theory side, I feel, not just from the field theory side that it is a free theory, but from the string point of view also, it's a natural expansion point.
In some examples, we think we understand that the string breaks up into bits. For instance, in the ABJM case, does that tie in?
Yeah.
Hopefully, I'll be able to say something about that by the end.
Just say one more time what's the connection between this 1 by n and the genus expansion that you're saying?
Yeah, so the 1 by n parameter measures the genus expansion. So for each power of the genus, you put in a factor of 1 by n square. So that's how you, in the field theory, you expand this in powers of 1 over n. It is in actually in increasing powers of 1 over n square. Each corresponds to a higher genus. The leading one is genus 0, then 1 over n square suppressed term is genus 1. Similarly, here, that's the parameter gs. Okay, so as I said, so I'll make there'll be a concrete proposal for the concrete example is based on a proposal we made for a particular AdS CFT duality, which is that the 2D orbifold CFT, I'll explain this. M is T4 RK3 is equivalent to, and so in a 1 over n expansion, is equivalent to string theory. So our so the whole context of this discussion will be a specific proposal which we made a couple of years ago, that that there's a essentially free two-dimensional CFT, which is something called a symmetric orbifold CFT. For those of you who haven't seen it, it is essentially you take some CFT on, say T4. T4 CFT means essentially there are 4 free bosons and 4 free fermions corresponding to the directions on the torus. And similarly, the target could be a K3, which will be slightly more complicated. But you take n copies of that CFT, and then you orbifold or by the symmetric group that exchanges these copies. And orbifolding is your standard two-dimensional CFT procedure. This has a nice 1 over n expansion, these CFTs. In fact, these CFTs have been studied in the context of black hole counting. And the thing has a long 20-plus year history of 25 years maybe of study. So this side is essentially a free theory, especially if you say take T4. It is essentially many copies of T4, which is free bosons and fermions. And then the orbifolding is a bit the analog of what you do in free Young mills, where you impose a Gauss law constraint. So you have to make some overall projection onto states. So that's the two-dimensional theory. So that's the free side, the free theory. And you can look at it in a 1 over n expansion. The proposal is that the dual theory is also a conventional string theory, but on an AdS3 times this 3-sphere times the same m, T4 or K3, but with 1 unit of a 3-form flux through these AdS3 and S3. So there's these AdS backgrounds are supported by these higher form flux fields. The AdS3 case is simple because you can actually support the AdS background by just having an NS-NS flux. This is something I think I don't have time to explain, but normally it's the Ramon-Ramon flux, which you have in these superstring theories. But this is a very special, much simpler kind of flux which supports this background. So this background is a background of type 2b supergravity, and it can have any units of the quantized units of these flux. we'll take the minimal number, which is 1. And there is no, you can in general have an admixture of NS, NS, and RR flux, but we'll take no RR flux.
So this is the, can I think of this as the near horizon geometry of
one NS5 brane and K and N these and fundamental strings.
And the NS5 brane is wrapping this T4 of the K.
Yeah.
Okay, the remaining non-compact dimensions are on the 1 plus 1 dimensions are not so big.
Yes. And it is S dual to what is called one D5 brane and N D1 branes, which is what the context in which this has mostly been studied. But that's why our claim was a little heterodox. But as we'll see, I think there's very strong evidence for it.
Sorry, just quickly. So on the bottom side, the AdS3 string theory side, you have a dilaton then?
Yeah. There's a dilaton, which is a fixed dilaton, which is proportional to 1 over n.
So it's actually fixed.
Yeah.
So central charge comes out right with K equals 1, etc. Does the S3 radius compensate?
S3 radius is also fixed. So you get C equal to 6. Yeah, so this is the target space of that CFT, meaning the CFT is that of free bosons, which are essentially compact bosons. And it's a, yeah, it's a, this thing, so it has, so if you wish, you think of it as embedding of the 2-dimensional CFT in this 4-dimensional torus.
In general, turning on some D3 brane charge
would be there are various moduli here. There are moduli and 20-parameter moduli space, which we of the single particle moduli, which will agree with the moduli over here. And we haven't explored that, except the T4 moduli are trivial. There will be 16 of them, which are trivial. Sorry? This is a 2D CFT. This is a AdS3 times S. This is the RHS, and this will be the LHS.
In this large illuminating thing, right? So how is it? I mean, are you putting this 2D CFT inside this CFT or what I said?
No. So the CFT is a 2D CFT, but it's just that the fields in that 2D CFT take values in the M. Yes. It's a hyperkähler space.
Only that, why do you give out M equals S3 times S1? Because that's also a nice sigma model background.
I think there are some subtleties with that case. There's because it has this large. I don't want to go into that. There is likely to be a story there. In fact, there are pieces of that story. It has not been completely sewn up, but there is likely to be a story there as well. Yes. Yes. You can do many of the things with this thing. Yeah.
So what is
One second. Huh?
the number of flux units has nice
Increasing the number of units of flux? No, this is not a marginal parameter. It's a quantized parameter. So yeah, so it's not very clear for k greater than 1 what is the dual. There is a proposal by Matthias and Lawrence which reproduces some part of the spectrum but not the whole spectrum. So they are talking of M times a Liouville symmetric product. It has some of the right features, but it's not completely clear it is the one, but yeah.
From the brain point of view, it would be K.
Hmm? Brain K and S5 brains, yeah.
So this large capital M.
Yes, yeah.
So when you
That in the string theory, huh?
from the CFT side.
Yes.
So it's what does it mean to take values in this product of M with itself?
No, first think of the CFT on M, and then you take a tensor product of those Hilbert spaces of that CFT, and then there's a certain procedure for bifolding in that Hilbert space. Yeah. Yeah.
Answer it just as the dilaton is fixed.
Yes.
So just
Near horizon geometry is,
so in connection with that, maybe you'll come to this later, but just say,
yeah.
if K was greater than 1,
Huh.
then the picture of space-time is far away, there's this flat space,
Yeah,
Then there's the linear dilettone throat.
yeah.
And then that throat, when the dilettone reaches 1 by n,
Mhm.
it gets capped off
Into
phase.
a ADS space.
Okay, but as you know, the traditional view is that there is no linear dilettone throat when k is equal to 1.
Yeah.
So should we think of this as just the flat space ADS joining onto ADS, flat space bar joining onto
Yeah.
ADS without an intermediate?
I think so. I mean, we've had this discussion. I think so, at least. But it might be good to see that approach. Yeah, see that.
So sorry, but for those who are not cognizant, why is it that for k equals 1 you don't have the linear dilettone?
Well, it's the usual reason that he's going to get an outcome.
No, yeah.
So it doesn't connect to asymptotic. It does connect to asymptotic.
It is the NS5 brains. The world sheet theory of the NS5 brains is a non-trivial world sheet in the NSR formalism. At least one non-trivial world sheet
For k equal to 1.
K greater than equal to 2. K equals 1, there is
No known in this thing. And we, what, yeah.
Negative charge, negative
I'll maybe come to part of that at some point. So I just want to make a couple of comments on this proposal before we flesh it out. Firstly, as I've said this before, this is purely NS-NS flux instead of Ramon-Ramon flux, and it's the only case I think we know, and this AdS3 is the only case we know with NS-NS flux. For those who don't know what NS-NS and RR mean, don't worry. The main thing is that with the NS-NS flux, the string worldsheet theory is in much better shape. You know how to, the worldsheet description here is under much more control. With the Ramon-Ramon, there are still many issues, which is why people haven't made so much progress with that. But so we are in a good, happy circumstance here. And in fact, this case with k units of NS-NS flux, the general case was studied by Maldacena and Oguri in building on earlier work also, but the culmination was, in a sense, the works of Maldacena and Oguri, which basically studied this worldsheet theory very thoroughly. And I will summarize some of the relevant parts of their work very soon. The other thing I wanted to say was, because this is the minimal, I said, of course, this side is free, but this is actually, you can see it as a realization of this picture, because with this unit of NS-NS flux, the string radius, RADS, is essentially, the ADS radius is essentially of the string scale. It is, at least with NS-NS flux, it is the smallest radius, in a sense, you can have. So it is the analog of the tension. It is as tensionless as you can get in this a set of theories. So,
Sorry, Rajesh. So I seem to remember, at least in the D1, D5 context, that GS was 1 upon n.
yeah, so this is GS square because it's the way in which, works, or the linear, if you look at the dilettone, it's.
Because the tension of D5 was like 1 upon G.
Yeah, you can trace it to that exactly. It's the NS5 brain tension, which is 1 over G string. So, okay. So let me say about this string theory as studied by Maldacena and Oguri. So the worldsheet theory. So this is now some summary of, a very quick summary. I would say I will not be able to do it justice. I can talk offline about many points if they are not inhibiting understanding. So the worldsheet theory is in the NSR description. It's an SL2R level K plus 2 times SU2 level K minus 2 times T4 CFTs. So these are CFTs which are Weissman-Witten models with these levels. This is, these shifts come basically because you're in the superstring theory, and therefore you can view the level K super Weissman-Witten theory as a bosonic level K plus 2 or K minus 2 where's the Minovithin theory with additional free fermions. So anyhow, those are this thing. So these are all individual pieces are well studied. This is of course very well studied. This is very well studied. This was not so well studied, but Maldacena and Oguri gave a very thorough analysis of what at least the physical spectrum in the string theory would be. So,
sorry,
huh.
we said it again, but k equal 1 makes the level of SU2
to a negative. So that's why, but right now I'm just summarizing what Maldacena Oguri did for general K.
K-dependent central charge cancels out.
Yeah, because 1 will be 3K plus 2 minus 2. And, yeah. So this is a regular NSR formalism. The spectrum, I'll just summarize. Essentially, they essentially work with the bosonic case. So when I say this, the supersymmetric case was worked out by various people afterwards. I think even Subrat has a paper, I think. But it was a generalization, various Kiritzes and others. So spectrum consists of, so that's why they did not even remark on K equal to 1 or anything. For them, it was purely they were looking at the SL2R level K theory. So you want to quantize the string.
Was not even there.
In their paper, they didn't even have any such thing because they didn't have this shift. So in their paper, yeah. Mm-hmm. In fact, there's an interesting, but that's a side I don't want to go into. There's something interesting that happens at K equal to 3 for the bosonic case, which is the same. But anyway, which they hadn't remarked also, but which we had a paper on sometime. So what do you do when you do a string? I mean, I'm hoping that Shiraz has taken his marathon classes on string theory and and people are all familiar with the abstruse parts of the abstruse identities and the what do you do in a flat space? What you have to do is firstly look at these are conformal field theories, first and foremost. You look at the Hilbert spaces of these conformal field theories. You have primaries and then the descendants, and then you impose physical state conditions finally to look at the string spectrum. But first step is to understand the CFTs and the spectrum. So the CFT spectrum, I will concentrate more on the SL2R part because the SU2 parts will sort of go along. So you have these representations of SL2 as the affine primaries, as the primaries of the CFT. What do I mean by that? So this is the global part of the symmetry, and SL2R as a Lie group. You know it has, unlike SU2, which has only these unitary discrete representations, here there are continuous and discrete representations, and both appear in, you need to consider both in the spectrum to get a consistent string theory. And so I'll introduce some notation which I will use later. The continuous representations are labeled by so these are these are continuous representations of SL2R, which are labeled by J quantum number. So the J is essentially, there's a quadratic Casimir, which is J into J minus 1, like for SU2. So this is like a J and M for SU2, but except that J takes the continuous representation, J takes values half plus I times P. P is real. You can take it to be positive. And then there's an M quantum number, which is actually, unlike SU2, it's unrelated to J. It's some specified by an additional parameter lambda. And then there will be integers up and down. And they're up and down. So that's why it's a continuous representation. It's unbounded from below. It's not highest, whatever. So these are the representations. Yeah, yeah. So these are the representations, the continuous ones. And then there'll be the discrete ones. I'll take one representative of that. These are more like the SU2 representations. They are given by, again, a number j, which labels the Casimir. But here the j is real greater than half. So j is greater than half, greater than or equal to half, and real. And this n, and the m quantum number is related to j, and let's say it's a highest weight. That's why I put a plus sign. So the m quantum numbers start from j and go upwards. There is another set which are dj minuses, but you won't really need them. Okay, so so you need these representations as your building blocks for the general case. So if you wish, think of these as the analog of, in flat space, you're labeling representations by just some k. Right? Ground state primaries I'll just label by some k, which is representing the Lorentz group, and maybe some spin quantum numbers and so on. So, so this is the analog of that in the AdS3. There are two quantum numbers labeling the states.
Is the last number the space-time energy in the end?
Yeah, it will be related to that because with spectral flow it will be shifted, but it will be related to that. I will come to k equal to 1, but first let me just summarize what they said for general k. The more unusual thing which I think they recognized. Yeah, you can think of AdS3 as the group manifold. The Lorentzian AdS3 is actually the SL2R group manifold itself, which is one of the reasons why that is playing a role. So you need these together with, so what you do with these is that, just like I said, you in flat space, these are the ground state things. There's some k, and then you act upon it by, in flat space, by oscillators, right? Here these are the primaries, and then you act upon it by the affine, let's say the j's are the generators of this. There are affine modes, ja minus n, j plus minus, and j3. And there will be also k, there will be some ka, which will be from the SU2, and there can be some torus excitations. But essentially, I'll focus on the SL. So there'll be these will be the stringy oscillator states that this is the bottom of the tower, and then there are this thing. But that is not the end of the story, and this is the whole interesting. What makes this theory very interesting and non-trivial, even at k equal to 1, as we'll see, is that there's together with the spectral. Yeah, 1 second. Yeah. Yeah, T4. Yeah, I mean they'll play a role later, but the T4 CFT is like a free CFT, so you don't have to. It doesn't play a very significant role. You'll tensor in the end things from all of them, but so there is an operation called spectral flow, which is there even for any current algebra, but it can be quite non-trivial in these non-compact cases. The spectral flow is to define, if you wish, operational way to think of it is to define new generators I define some new set of generators, J tildes, built from the original generators by this redefinition. This new J tildes will also satisfy the same current algebra as the original J's. Okay? W is we'll take, so W is we'll take to be belong as a positive integer, let's say. Yeah, so W will be positive integer, which will label the spectrally flowed sectors. It is related to these W's that I wrote earlier. So the thing is, okay, this is just some redefinition of generators. But what is non-trivial is that starting from a representation like this, you can define a new set of representations, inequivalent representations, in which are annihilated by now J tildes. They are primaries with respect to J tildes and not with respect to the original J's, therefore, because this is shifting in the modings. And so you get these whole new sets of representations. And what...
Do you have any intuitive way of thinking of this process?
Maybe, hopefully later, then this picture will become... Yeah, I think there's a very nice geometric picture and so on, and which will relate to the twisted sector states, etc. But hopefully I'll... Yeah.
Also, this, so at least the continuous parameter by this, by this relabeling, you have a rule by how it changes. So you're going to...
Yeah. So you can, I mean, because there'll be you can work out the quadratic Casimir. It will have some shifts and so on. Yeah, so there's a very definite rule by which it be related. The quadratic Casimir will be, essentially the C2J was the quadratic Casimir that's built from, okay, not the C2, that's the zero mode part. But in general, there's the so-called stress tensor. But yeah, you can look at the zero mode part also, that will have a shift and so on. Yeah, so the labels will have... No. I mean, they will... the LNs also get a shift.
So in the end, representations are labeled by these labels plus W.
Plus W. So what we will have is these. So there will be an additional W label as well.
So the representations, the highest rate representations for some non-zero W, can they be thought of as sub-representations of zero W algebra?
No, they're not sub-represented because these are...
Sorry, some representation. Not necessarily highest rate, but some representation.
No, they are... yeah, not highest... Yeah, okay, they're not highest rate, I don't know. Yeah, I mean, they are in some sense representations, but yeah. Yeah. SU2, the thing is that it just reorders the labels. So it just, what you called highest weight becomes something else, and it kind of just permutes the representation around. So it's not a trivial, because, yeah, so there's no non-trivial representation you generate by this action, which is why it doesn't really play a role in SU2 Weismann-Witten theory or anything. Yeah, in that case, the Casimir is the same. So
we can think of the spectrum flow as just a convenient way of
getting new representations, and it turns out, and I don't have this thing to this thing. So this is at the level of the current algebra, but it turns out that this is the space of representations you need to work with to generate what is called a no-ghost spectrum. You want a spectrum of physical states which is unitary in the end. Because in fact, this was the non-trivial challenge that Maldacena, Oguri, and everyone had, because SL2R is a non-compact space. It's not like in flat space where you can go to light cone gauge and just one transverse oscillator and one longitudinal oscillator cancel each other out. It's here there is a time-like direction which has negative norm. There are space-like directions. How do they exactly all balance out so that there are no negative norm states in the spectrum? This was non-trivial, and they showed that if you impose the physical state conditions, which are essentially in terms of the usual, in NSR formalism it will be, and then ln. for n greater than 0. So if you impose these conditions and the appropriate GSO projection and all that, I won't, I think, go into all that. If you impose this and you have this thing that in the supersymmetric case, the J, okay, for the discrete representations, J lies in this band between, not 0, half and J and K plus 1 by 2. If J lies in this band, then you get a ghost-free spectrum. And so this is what they showed, and it was very, they had non-trivial checks. They worked out the one-loop partition function, many things that this gave you the consistent string spectrum background for the whole thing. So yeah, for the fermionic string. So there's new parameters, 0 or half, and all for depending on Ramond and Neveu-Schwarz, NS sectors, etc. Omega equals 0 in Gerard, there are discrete states for omega equals 0.
But isn't it ruled out by GSO?
No, not in general. For W, no. I think for discrete states you have unflowed representation. For continuous, I think it is.
Sorry, Rajesh, I didn't understand. So this is the restriction on J given any K. And what about omega? What is the restriction?
No, omega W is any
Any can be any.
anything, any positive integer.
Sorry, L also you said has a W label.
L? Sorry, what?
You said L also has a W label, right?
L, if you express it in terms of the this thing, yes, you'll have a. But ln is ln, and there is the original ln, the Virasoro, the stress tensor. That is the stress tensor.
Morphism of the W action of fusing it with constructing.
Yeah, that's right.
So when you say this, you mean a particular peak. You pick a particular J, right? To think of this as a Sugawara stress tensor of a particular
For
choice of W.
yeah, for each W you impose this, and you construct the L0 based on I mean, so the L0 will be the L tilde 0 with some shifts. So the physical state condition knows about W.
Right. But this is, you pick a particular W to do this projection. Or
No, I mean, it's the state. The state carries the information about the W. Yeah.
Spectrum is labeled by W, J, lambda, P lambda the continuous thing.
Yeah, P lambda for the continuous thing, and J and J for the. Sorry?
in this
L0 is the usual, just the full stress tensor of the Sugawara stress tensor. For see, the stress tensor is independent of what W is or anything, right? I mean, in the sense that
depend on that, right? Modes depend on
that's a way of, you can slice it up in various ways.
N equals 0 is a slice, right? N greater than 0 is a slice, right?
Yeah, so you work with the modes. I mean, what I mean to say is that you can relabel all the modes in whatever way you want, but there is a stress tensor for the full theory, and these are just different representations. You just act by that same stress tensor on those representations.
So in other words, this automorphism does not mix positive modes with negative modes?
Positive modes with negative modes.
Of the stress of the L's?
No, I mean, this is the ln's. So ln will be whatever. You pick up those n greater than 0.
I
Right?
think he's asking, is ln greater on physical equal 0, same as ln tilde?
No, it is not.
No.
It's not.
So what do you mean when you say Ln?
No, ln is the mode of the stress tensor, right? Stress tensor is an operator in the theory, so you can.
Think of this just as a trick of generating new representations.
Yeah. Yeah.
Forget
So in other words, W equals 0 choices.
Huh? Yeah, you can, this is just a labeling. In the end, you think of the states as being defined by actions of J's in some way, that these modes annihilated, these modes don't. You can forget about the tildes altogether and say that there's a set of representations with these are annihilating and these are not. Yeah, so I just want to give a beginning. I mean, I'll explain more the the physics, spectral flow, and so on, a little more as we go along, I think. But I just want to say one thing about these states, the physical meaning of these states. So Maldacena-Oguri proposed these states. So they have a nice physical meaning. So AdS3, if I think of as a ball. The discrete states are like the usual discrete states in AdS. There are, because it's a box, there are some finite spectrum, box-like spectrum discrete states. But there are additional states, and this is special to AdS3, in which there are strings which can, kind of long strings, as they are called, which have a tension. So normally you would think the string this will be very heavy states, but actually because there is this three-form flux, you can balance. There's an effective tension, and so you can have a finite energy excitation, which is very macroscopic in some sense, and which can have momentum. And this P labels the momentum, a radial momentum of those strings, and this W can be viewed loosely as some winding, that it's not a conserved quantum number, and indeed it isn't, but you can think of it semi-classically as that there's a string which is wound W times around the, let's say, around the boundary. No, it's not a conserved number, because the AdS is shrinkable. So you can't, there's no winding number.
Sorry, if you excite this primary, then what happens?
I mean, what I mean is it's not conserved in the full string theory. String interactions can change.
Interactions can change.
Yeah.
But I mean, okay, as a one particle state or whatever.
Yeah, so it's a good quantum number, which in the non-interacting theory, it is a quantum number.
And the interpretation as winding is clearest for the continuous states,
right?
Because they go off to infinity,
Yeah.
and then the winding is very
Yeah,
clear.
exactly.
So the discrete guys, it's
Yeah,
less clear?
yeah. So discrete guys, I will not have anything more to say about it because the discrete guys will not appear for me. So,
Sorry, I should
yeah.
do this, but for the continuous guys, if you just write down some DPI type of action and so on, you can see these states.
Yeah, exactly. Semi-classically, there are, in fact, I will say a little bit about the semi-classical picture of these tomorrow. But just question about the discrete states. One way to understand it is from this bound, that when you reach the upper part of the bound, you essentially go to the next spectral. So in such a bound, for the discrete spectrum, there's a finite number of states. But when you go to the upper part of the bound, what you do is you go to the next W. So it's a way to kind of put together different discrete states all together.
Then what that has to do with winding is less clear.
Yeah, it's not very clear. It's some microscopic winding.
Or is it just a way of getting states where J goes to the next band?
Exactly. So it is that, but that band winding is, maybe they are microscopically wound states or something. Lambda, which?
The lambda plus n quantum number.
Lambda plus n. Yeah, so now, okay, so this is for the representations. Now when I impose this physical state condition in particular, this is the what's called the mass shell condition sometimes, which essentially, because L0 plays the role of the Hamiltonian. So this is what this condition essentially for the continuous states gives you, for the discrete states, what does it do? Okay, let me step back. For the discrete states, it gives a relation between the J's and it essentially tells you that the M, so M, as Shiraz asked some time back, actually M plus KW by 2 because of the shift is the quantum number for the space. The J, this J is part of the SL2R, right? And part of the SL2R in space-time is the space-time L0. And so that space-time L0 is J3s here. Right? Because it is the third component, it's the Casimir of the space-time SL2R. And the space-time SL2R is what is giving you the space-time conformal dimensions. So the conformal dimensions are in space-time, or the energies in space-time are actually, so the spectrum that you really need in space-time is the spectrum of J3. So the mass shell condition fixes that because it fixes J, and it gives you typically one relation which fixes, you can think of as fixing J if I fix the SU2 quantum numbers. And fixing J then fixes M, essentially. I mean, you have integer spaced ones.
Sorry, that value of J3 is M plus K omega.
Or M minus K omega, depending on this thing, yeah.
And of course, it fixes J in terms of the quantum numbers
Of the oscillators, in the T4 and the SU2 and so on. So there'll be a J prime for the SU2. SU2, there'll be a label J prime, and T4 will have its usual momenta and so on. So it will be L0 is a sum of all the L0s of the SL. So when I wrote this, it's the sum of the SL2R, L0, SU2, T4, everything. Similarly here. And so this condition gives you a relation which relates the Casimir of this, and then all the excitation numbers.
What exactly are you saying that this is a winding number about?
It's not a real winding number, but if you wish, if you can think of a large string which is sort of wound W times, or if you wish.
So is there some integral that you can compute?
No, it is not a conserved number, but the closest you can do is think of it like we'll do it on the boundary. You can wind it. You can think of a winding of the world sheet. Let's say the world sheet is a sphere, then you have a sphere to a sphere, and that will be wound W times.
Otherwise, it can always be unwound.
In the bulk.
Of course, yeah.
Yeah.
So basically, you are removing some.
Yeah, in the middle and then.
And Rajesh,
Yeah.
you said it just to understand. So there are descendants of the Casimiri algebras which are still primaries of omega 0, and the full spectrum includes all those.
Yeah, exactly. So, okay, good. I should be moving faster. So the.
I have a naive question. If I put a black hole, then winding number is conserved?
I mean, of course, the spectrum is not quite the same in the first place, but yeah. So you might naively think so. I don't know if anyone has really looked at that in a. Yeah.
You mean Euclidean?
Probably, right? Yeah, in Euclidean space. Because
It becomes some winding, yeah, in the time circle.
Yeah, because it doesn't happen if I have a massless BTC, it doesn't happen that its winding number is constant. That's why I'm asking. Because there I also have a singularity.
Yeah, I mean, yeah, the thermal AdS. I mean, this thing what Shiraz said, when you do an S dual, that one would definitely have a winding quantum number. But yeah, so I don't have a very good answer to that question. So anyhow, let me conclude the Maldacena-Oguri analysis. So it's a beautiful analysis. It gave this full description of the spectrum, but it showed this, one second, it showed that there's this sort of singular behavior in the spectrum. Namely, there are these continua. So the spectrum is labeled by a continuum. So I mentioned the discrete states. When you impose the mass shell condition, it just gives you a relation for M, and there's a discrete. But here, because there's P and lambda, and this was Abhijit's question, which I didn't fully answer. If you have, because you have P and lambda, the mass shell condition, you can say, uses it to fix lambda, but it doesn't fix P. So there is still, in the physical spectrum, there is a continuum. And that's the P. So this spectrum of this whatever dual CFT must have a continuum. but 2D CFTs have continua like Liouville or free theories and all, but you would think that if there's a, so unitary theories, difficult to see how it happens. So
for Mn over Sn or something, why would you expect?
yeah, so for Mn over Sn definitely doesn't have a continuous spectrum. This one knows for T4, I mean T4, K3 are compact spaces and nothing, no continuous spectrum there. So that's why of course no one tried to connect these two. People thought it's somewhere on the moduli space, something, lots of talk. I mean it was.
There's a line in a paper written, I take this to mean that this is bi-rationally equivalent to that. Whatever that is.
Yeah. So this is indeed we have no quarrel with that picture, Maldacena-Ogori's picture for k greater than 2, greater than or equal to 2. But what I want to claim is that for k equal to 1, things are very different. This picture, not very different, but this picture undergoes is to be refined more. Now it's very difficult to do it in this because, as people have already observed, k equal to 1, this level becomes -1, and so it's a little tricky what that means. So what? Well, in an early paper, which I don't want to go into.
Before you, if there is a 10-second answer,
yeah.
Is there any way of thinking of this lambda parameter? Is there any?
Lambda is like the m parameter. I mean, it is the m parameter because this is the J30 quantum number. So it gives you the space-time dimension because the Marshall condition relates lambda to p. So essentially, it gives you the space-time dispersion relation. That gives you the.
But normally you have this idea that you have something plus integer spacing because it's like a box.
Mm-hmm.
Now these guys are going out to infinity, so they're not behaving like a box. And still there's some discrete thing plus integer.
Yeah, so the discrete things are, I think, oscillators around the. Lambda is the center of mass. Lambda, if you wish, you can interchangeably think of p and lambda once the Marshall condition is imposed. It's a continuous parameter, and you interchange it, so there'll be a continuous parameter. But then there's a sort of a spectrum around it, so it's like, I think you put little wiggles on these things. I think that and that is the discrete spectrum around any of these. Mm.
This continuum in the brain picture is this separation between the NS5 and
Yeah, so that's another physical way to think of it, that there's this branch that is there you can separate it without any cost of energy. So that was how people.
You move the NS5s into the.
Yeah, in this thing.
Isn't that different?
This the fundamental strings.
I mean, is that a no? That is a.
It's on the Coulomb branch. I mean, it's.
No binding energy.
Yeah.
No binding energy.
So can I think of lambda as saying that these are projective representations? Because in Euclidean space, something lambda would have to be an integer to be well defined as you go around the time circle, right? I mean, if you think.
Yeah.
And then. Okay. Anyway, forget it. It's not.
Mm-hmm. Yeah, I'll talk later. So the thing I want to at least, I think. So this k equal to 1 theory, if one has to make sense of it, so I was saying we tried to make sense of it, and there is perhaps a way to do it in the NSR formalism, because this SU2 level -1 has a you can think of it, it's a non-unitary theory, it has central charge -3 or something, but you can think of it in terms of some beta gamma like system. So we tried to do that, and in fact we found quite remarkably a way to match the spectrum to the symmetric orbifold, but it was a little ad hoc and prescriptive. But there is I think a much better way to address the k equal to 1 case, which is to consider the alternative description, which is called the hybrid formalism, and in this particular case due to Berkowitz, Waffer, and Witten, which is like these Green-Schwarz variables. So these are variables in which the space-time supersymmetry becomes manifest in AdS3 times S3. So it's called hybrid because it's a way in which you make the space-time supersymmetry manifest on this part, but keep it sort of NSR on this part. And so what they argued in this alternative description, which actually extends to the case of Ramond-Ramond flux as well, which is why they were very they advocated this approach, is that you can consider by doing certain changes of variables and so on, you can write it in this Green-Schwarz form, and they argued that the theory on AdS 3, so the string theory on AdS3 times S3 times M is equal to, with NS flux, so they sort of made a change of variables effectively on these NSR worldsheet fields, and that change of variables, they for the case of pure NS flux, essentially took the AdS3 times S3 piece into a super group, which is PSU1,1/2. So a PSU1,1/2 is a super group which has a SU1,1 here, SU2 here, and some fermions here. I think S's, and such that the whole thing satisfies whatever, it's a unitary matrix. And the P and the S's are various sort of diagonal projections, I mean, taking out various traces. So this supergroup, there's a very nice picture, because this supergroup is really the space-time supersymmetry. This, the group itself, PSU1,1/2, is the space-time supersymmetry of AdS3 times S3 with maximal whatever the n equal to 4 supersymmetry it has.
This does not depend on whether M is T4 or K3.
Yeah, that part is this thing.
The
Yeah.
complex structure is.
Yeah. So it's very nice in that the space-time supersymmetry now gets manifest, because the zero mode part of this is the space-time supersymmetry, so that's what the Green-Schwarz like formalism does. There's some ghosts. So this has central charge equal to -2. These ghosts have C equal to 2, and this is C equal to 0. So there's a critical string background which has all these ingredients. And for the case of pure NS flux, it is also a well-defined string background. This is a supergroup Witten model. These are some simple ghosts, the free ghosts. In fact, in the case of the nice thing about the NS case is that the ghosts are decoupled from the matter. It's a simple ghost system. This is just the T4 theory with a little twist. But
how many there are 4 complex supercharges in this thing?
4 complex supercharges, I think.
So I should think of half of them as being supersymmetries and half of them being
conformal from the boundary point of view.
So 4, so that is one, the full system had 1/4 of 32, right?
Yes. So 4 complex, right? You said so. That what I mean, I think that's 8. I think. No?
But the full system had 1/4 of 32 without counting the super conformal enhancement. Right, because you put NS5 braids, that's half.
Right.
Fundamental strings, that's half more. So there'll be some other supersymmetry somewhere.
No, I think this is the whole supersymmetry. PSU1. I think this is.
8 supersymmetries and 8 superconformals.
Yeah, no, I think the whole thing is there in this. This should be because there's a 2x2 block, and then there's 4 and 4 complex 8. Okay.
Yeah.
4, 4, 8 complex.
No.
No, not 8 complex. I think because I think there's
Yeah, 4 complex,
because it's diagonally related. 1, 1, 1.
Yeah.
Yeah.
Sorry, this doubling is in the low energy, right?
This is the.
Yeah, it is the CFT. It is the.
It's 2 is what I'm saying. That from you take NS5 braids and fundamental strings.
Yeah.
Each breaks half supersymmetries. It's 1/4 of 32. So that is 8.
Yes.
Then you expect that when you put it in the AdS background to get double. So you get 16. But here I can see only 8.
Yeah, I'll have to trace that through. But it is this. I think in the case of K3, definitely you break more.
And therefore, the other thing has, in the case of T4,
For us to be some T4 fermions will probably create some additional supercharges. That's right. So, okay. I know we have a cut off, but as long as you're here, I guess I can.
It's only at 2 o'clock.
Yeah. So this thing. So this is the proposal they made, and the nice thing about this is that this is well defined even at k equal to 1, because it's just a supergroup at level 1, and
K equal to 2 would have had some problem then.
it would be trivial. It would be trivial. Yeah, so I think that it is interesting case. The S3 part is not there in a real sense, but at least there's no obvious problem. I think the continuum will still be there, but that's a sort of a somewhat interesting case. I don't know what to make of it, but.
So the RNS formalism doesn't quite work.
Yeah.
You can use this sort of GS.
This GS type formalism, and there's a reason I think which I can say later maybe, but because it's a very subtle this thing, because it's not a simple analytic continuation to k equal to 1. That's why so the sigma model is well defined. For k equal to 1. But one very interesting thing happens at k equal to 1, that in general, a long multiplet, multiplets of the space-time supergroup. These multiplets, let's say I look at the continuous part, they have, you can label them by the continuous part, the CJs that I wrote, and some n, which is the SU2 label, which is the multiplicity of the SU2 representation. So these multiplets, so these are the bosonic thing, but a multiplet of the full group has many of these. In fact, you can work out how many it has. It has things with, supposing you have J, some J naught, it will have J naught plus minus half, J naught plus minus 1. And similarly, N will be some N naught plus minus 1, N naught plus minus 2. the supercharges will create things up and down. So these are the generic multiplets. There's some truncation when n becomes, n and j are small, when they are 1 or 2. But still, they are long kind of the longish multiplets. But
So what was n again?
n is the SU2 label.
Like j of s.
Yeah, it's 2j plus 1.
Yeah, okay.
It's just the multiplicity.
So this plus minus the thing that you wrote is the
What you get in the multiplet, huh?
composition into the SL2R representation.
Yeah, you decompose the full multiplet into representations of SL2R times SU2, you get these sort of, so you get a whole set of multiplets. So this is the generic multiplets. And these are the things that you would have as the basis for your states for general K. But then there are also short multiplets. So there's a sort of a super short multiplet.
The level only figures into picking up the integrable ones.
Sorry, the level?
Only figures in this thing in an
Yeah,
isolated
yeah,
subset.
exactly. Yeah, and so that's what I'm saying. So right now, this is just about the global supergroup. What is the what are the multiplets? There are also super short multiplets, which are labeled by C half lambda 2, C 0 lambda plus half. Sorry, lambda minus. I think one of them should have. No, it's lambda. Still lambda plus half. Yeah, it doesn't matter. And C 1.
What happens if you change k from 1 to larger values? What happens to short multiplets break into long ones?
You mean the long multiplets break into short ones? No, which one? No.
This is for k equal to 1.
No. This is just, I'm talking about the multiplet. Like, a super multiplet has many pieces. Just decomposing multiplets of this whole thing into their smaller this thing. So, but there are these, I'm saying there are very special short multiplets when j is equal to half, which the multiplet only contains three multiplets of SL2 times SU2, whereas the generic one here contains many more.
And this statement does not depend on k.
No, this is just a statement about the representations of the global PSU1, I'm just saying there are multiplets like this. In fact, these multiplets are ones where, so these short multiplets have this thing that the super Casimir of this thing, the C2 is equal to 0 of this. So I will call this multiplet F lambda. This is a super multiplet. It's labeled by lambda. I'll call it F lambda. So there's a super multiplet of this F lambda. Has the super Casimir vanishes. The bosonic and the fermionic pieces of the super Casimir. Super Casimir is has the Casimirs of this, Casimir of this, and Casimir of the fermion, quadratic Casimir. So these vanish, and that's a nice property of this thing.
So this is for the old, super short multiplet only, right?
Yeah, this for the super short multiplet only.
Where have you put k equal to 1?
Nothing. So far, I'm just making some group theoretic statements about the supergroup.
This is valid for all k so far.
Yeah, I mean, it's not even, it's a statement about just the group, not
the
even.
global part. It's not about current algebra.
Yeah, it's just about the zero mode of the global part of the group. Now I will say,
Interesting statements when k is turned on about the current algebra.
I'm going to say why this is relevant for the current algebra. So the relevance in the current algebra is that, so you know that now you have the current algebra. Okay, this is the multiplets. Now consider PSU 1, 1/2 level 1. It has inside it an SU2 level 1 current algebra also in it. And because it's a SU2 level current algebra, I remember I called these Ks as the SU2 generator. So I think there's some K minuses. There's a null vector which is at level 2 in SU2 level 1. That's what tells you that the only j equal to half representations are allowed. So there's a null vector in the affine representation.
SU2 sector, which is related to that half. Which is related to that half.
Yeah, exactly. So I'm coming to that. I'm just saying that in general there is a SU2 level 1, this thing which has this null vector. Now you act by the supersymmetries on this null vector. There is you'll find there is another null vector which in that multiplet there is a null vector, another null vector which essentially expresses this for the which demands that the super Casimir is 0, because you'll have another null vector which involves L minus 2s. You can write in the supermultiplet form sort of a supersymmetric partner of this null vector is a condition which essentially imposes this. So essentially this is saying that the when you're at k equal to 1, the multiplets must essentially obey this condition. And you have only the short multiplets. Another way to say it is, a more pedestrian way to say it is by just looking at the SU2 quantum numbers itself. And the only ones which have nothing more than 2 is this multiplet. Any multiplet like this, you will have the J quantum, the SU2 quantum number will go more than 2. So it's so the only so these are the only allowed multiplets. Yeah, at level 1.
Sorry, I didn't understand. If I SU2 multiplet went above 2, what was the problem?
Just like for SU2 level 1, you don't have any don't have unitary representations.
No, but the SU2 is actually not level 1, right?
No, in this it is. In the other one it was shifted, but here you see the fermions are actually in the fermions are in this bifundamental representation. So you cannot decouple the fermions from this thing. It's not like the super SL2R and super and this thing. So the SU2 is really at level 1. Everything is just at level 1.
And why was it a good thing that C2 of FL was 0? That was important for some reason?
No, this is a nice invariant way of characterizing this multiplet. In fact, it's an if and only if. The multiplets which have 0 Casimir are these, and these are the only ones.
And C2 will go into the physical state condition?
C2 goes into this null state condition. So this implies actually C2 of the multiplet must be equal to 0.
But when we also look at physical state condition, will that only depend on the multiplet through C2?
There will be a part which will be C2, yeah, and then there will be other parts which will be, but there will be.
It's not just C2 from the AdS3.
No, because there will be all the spectral flow thing will all be there, and yeah, that's why.
Lambda will still remain undetermined. So in level 1.
Lambda remains undetermined at this level, at the level of the current algebra.
But now if you put physical stress condition,
Then lambda will be determined, and I'll come to that later.
so
Yeah,
now we'll lose that continuous.
exactly. That is the whole point.
That's what you want.
Right, right.
Will they participate in the recombination?
Who
The short guys
participate in?
recombining into long multiplets?
In principle, they could. I think in higher K they would. I mean, they can here, but there isn't anything to combine into. But not this multiplet. I think this multiplet cannot combine into long because you need higher J's. You may need multiplets like these, but other multiplets like these to combine. But purely these, I don't think they can combine.
So, at k equal to 1, if I just try to look at the AdS picture, I know that
the radius is sort of 1. It's all 1. I mean,
Everything is of the order of
Yeah.
even
Yeah.
the SU2.
yeah. Which is, of course, what the geometry also tells you. The near horizon geometry, the AdS3 and S3 radii are related, are the same. And so,
Not from here. Right?
yeah, so this picture is bad. This picture is, okay, I can talk later about why I think it is bad, but that picture definitely is not. You cannot.
So one can understand this level shift by starting with the super level -1 and adding 2 fermions from the superalgebra.
No, it's not so simple. You have to do this funny, all these redefinitions, Berkowitz-like redefinitions, which are quite this thing. Yeah. And then you have to put in the ghosts and everything also. It all mixes up. That's why the ghosts here are different from the ghosts there.
Wait, so the final statement was that the sigma model at level 1 has only these representations,
Yes.
just as a CFT statement.
Just as a CFT statement. Yeah. I think it's just like SU2 level 1 has only unitary representations with j equal to 0 or j equal to half.
This kind of truncation presumably holds for other supergroups also, right? The truncation coming from the compact part
Yeah.
at some small level.
Yeah, presumably. Maybe. I don't know if, yeah, maybe. Yeah.
I'm sorry to
Yeah.
but maybe this is lack of education, but when I learned that in SU2 you had only particular
Yeah.
spectra, I used unitarity for that.
Right. So that's why you have this null vector. Otherwise, if this is in this thing, there'll be negative norm and so on.
But as you were saying, I mean, negative norm may be removed in the end by physical state conditions.
Mhm.
So is it clear that we should not be considering other states as well, and then check whether physical state condition makes it?
Yeah, in principle, we have not looked at that possibility of looking at the.
They will leave even after the intersection. What is it?
Well, I mean, it could, as a theoretical possibility, it could be that you need that the full spectrum includes other states that are
Non-negative norm, yeah.
Right.
from the CFT point of view, but once you do the physical state condition, you still have a no-go state.
Could you comment on the normalizable, whether the states are normalizable or not? Because I remember that this continuous states has from Malazine algorithm, they had some huge comment on whether it's normalizable or not at different values.
Yeah. So here, these are more like the discrete states at the bottom of the continuum. And they are marginally normalizable, meaning they are, j equal to half is sort of the marginal thing of the normalizable. Because when you look at the norm, you'll get, when you square it, you'll get, it's the thing, I mean, j equal to half plus epsilon would be normalizable. So it is sort of just on the margin of normalizability. It's, so I guess you should just think of it as some delta function. No.
But on the other hand, if I look at the orbifold thing, the boundary orbifold, there the vacuum is, the states are fine, right? They're exactly normalizable. So, I mean, how do this normalizability argument work? Because on one side I have this almost normalizable thing that you are saying, and on the
Right.
orbifold I know that they're exactly normalizable.
I mean, yeah, I guess they are. Yeah, the normalizability is a little tricky because I think, the discrete, if you approach this as a limit of the discrete states, then they are sort of, then they are normalizable. And in the end, the ghosts will remove the parts from the AdS3. So in the end, I think there's no wave function on the AdS3 piece. So in some physical gauge, I think there's nothing on the AdS3 times S3 except some
You are saying everything is in the
T4.
So
That is the part
just
which
not
is
one.
the normal, yeah.
I mean, isn't another way of saying it that normalizability, things are non-normalizable because of delta. Just plain wave is non-normalizable because
Delta
of delta
function.
of P1, P minus P2. Now, if you have only one momentum, you can choose your normalization of that state to be 1. It's the relative normalization of different P's that makes it normalized. Here, there's only one P.
Okay, so so in the I wanted to let's see the thing I want. By the way, another way to see this, and this may be answering your other distinct question about the truncation, is you define, there's this free field representation of this PSU 1,1/2 at level 1 in terms of some free fermions and some beta gamma like system. Now, in that free field representation, it's like the fermionic representation for SU2 level 1. Now, if you take that as the definition of your CFT, the free fermion representation, or the free field representation of your CFT, then it automatically has only these states.
Okay.
So I think I would say I define my worldsheet CFT as that this thing, and it gives rise to a good spectrum, and this thing. So at least, yeah.
BRST with all these things will probably give you that CFT.
If you, let's say, work with the free field realization of this, there'll be, yeah, it'll have only these states, and then it'll the BRST cohomology will have only know about these states.
So you're saying there may be other definitions.
Yeah.
But you choose this one.
Yeah, and it's a critical string theory. It has the right feature.
Maybe from that point of view, the issue of normalizability also goes away.
Probably, yeah, because in that case it'll be just some fermion this things, yeah.
Rajesh, I just
Yeah, I think that's why I think maybe I will stop here because I think the last thing I wanted, I'm almost, I mean, I've done probably 85% of what I wanted to do, which is the last part was putting this together to see what the spectrum is. And maybe I can just start at the beginning of next class and start from there. So, okay, thank you.